Assalamu alaikum students and welcome to another lecture of Slate. This is me, Khawaja Yasin. Let's study chemistry. In the last lecture of transition elements, we talked about how important transition metals are today as of the CIEs. Because in the P4, I can easily vouch for the fact that more than 25% of the paper or almost 25% of the paper will be constituted of questions from this particular chapter of transition metals. Now, when we talk about transition metals, yesterday we talked about how they are D-block animals in the previous video. And furthermore, we just talked about their variable oxidation states. Why do they have the variable oxidation states? Then there were three other properties. And one of the properties is that they're used as catalysts. Transition elements are used as catalysts. Now, the reason for this property, this chemical property, this role is because of their very variable oxidation state. It is because of the fact of the oxidation state, they can not only serve as catalysts, but also as oxidizing agents. Strong oxidizing agents, not just oxidizing agents, strong oxidizing agents. Let's talk about the example of manganese, for instance, or just say iron. But for that purpose, you need to go back to the topic of electrochemistry. I hope you remember the way you write the equations in electrochemistry, that at the right side, at the left-hand side, you write the more oxidized form, which is a reversible reaction. And on the right-hand side, reduced form. So, more oxidized, your oxidized form, or this is the reduced form. So, whenever making this equation, you have to ensure that oxidized form is on the left side, reduced form is on the right side. And as I said, let's go back to the topic of electrochemistry. Such equations have an E naught value. An E naught value for this is 0.77 volts. Let's recall the concept, and I would like to reiterate the electrochemistry here because that would make that concept and this concept stronger together. That is what we know about the E naught value, and it's in positive. So when it's in positive, it's more forward. The reaction is more forward. Whenever it's more positive, the reaction moves forward. But when it's more positive. On the other hand, let's take another equation of manganate ion. You need to calculate, you need to know as well, this is an older concept, but what is the oxidation state of manganese in manganate? You just simply take manganese plus 4 into minus 2, which is the oxidation state of oxygen, equals to total charge of this, which is minus 1. So Mn is minus 8, minus 1. Manganese is minus 1 plus 8. Hence, this is manganese with a plus 7 state. Now, if we use this manganese in this equation, we get manganese, Mn plus 2 ions. We get 4 moles of water. And on this side, just to balance out, we take 5 electrons. That is what we know. But the E naught value of this is plus 1.53. Now, recalling the concept from electrochemistry, this value is more positive and this value is less negative. So, when it's more positive, I said this would proceed forward. And this less positive, it would proceed backward. So, if you look at the equation, more positive is moving to the right hand side and it is getting reduced. So, this is the reduction half. And this is the oxidation half cell. As iron 2 is becoming iron 3 here. So that is what we know about that. If we merge the two equations, this equation having the more E naught value will now be an equation with a single arrow, not a reversible equation anymore. Because due to this E naught value, we finalized its direction and it's moving forward. But the iron equation, the equation with iron, that is going on a different route. So we would rather use iron here, iron 2 here, since it's going backwards, and iron 3 here with 1 electron. And we'll multiply this whole equation by 5 just to balance the electrons. 5, 5, 5. Electrons get cancelled. So manganate plus now you can see that how by having these variable oxidation states, they can exist in both forms. Remember, in the last video we talked about how manganese can exist in +1, +2, +3, +4, +5, +6, +7. But why are we just talking about +7 and +2? Furthermore, sometimes +4 is also important. But why not the other values? Why not Mn +5? Because they're not particularly that stable. Even iron will have more states. But why iron 2 and iron 3? Because these are the stable ones. That we would study in the topic of stability constant, the K-stab value. That would tell us that why Mn +2 or Mn +7 is more stable, and that will be the one which will exist in nature. So we find out that these are the values, and using the concepts from electrochemistry, since we are doing it, how will we find out the E naught cell? Red minus ox, redox. So reduction half cell minus oxidation half cell, 1.53 minus plus 0.77, and that would give me a value of 0.75 volts. It's a positive value, therefore it can easily take place. It's a feasible one. You can easily see that manganese Mn +4 is getting oxidized, reduced, Mn +7, and iron +2 is getting oxidized. So that is what happens. How will we identify that? This is happening. But we are going to identify with the help of the color change. This has a purple color, Mn +7, and this is colorless. On the other hand, this is green, and the final solution will have a brown color because of iron +3. So the color change will help us find these things out as well. So that is how our transition metals, their oxo compounds, can serve as good reducing or oxidizing agents. What are oxo compounds, since I have talked about the term? Compounds containing oxygen. These are the complex compounds containing oxygen. I can also call them complex compounds containing oxygen. For example, as we talked about, the manganate ion. Or the dichromate one. So they have oxygen in them, and these transition elements have variable properties. For instance, if we use this dichromate as well, let's do an equation for this dichromate one. This has chromium with a +6 oxidation state. So if I have Cr2O7, 2 minus, and I use it with 14 hydrogens, you do not need to memorize these equations. You always get them. You never need to memorize the E naught values as well. You will get the equations, half equations, you will get the E naught values. So no need to worry about them. But we can use them to reiterate the concept. 6 electrons, again it's a reversible reaction. And that would ultimately give us 2 chromium plus 3 ions, 7 waters. And the E naught value for this is 1.23 volts. Now if I compare it with iron, this is also positive, iron was also positive. But if I compare the two, iron is less positive. So iron will be the reducing one and this will be the oxidizing one. So iron will be the oxidizing one and this will be the reducing one. So this will move forward. And if I just compare it with iron, this time we're going to multiply it by 6, 6, 6 so that we cancel out the electrons. And ultimately the final equation would be just adding all of them together. So here we can see that how these transition metals having variable oxidation states can serve as good oxidizing and reducing agents. But the story doesn't end here. We are mainly talking about the fact that how can they be used as good catalysts. As you see in this equation, that iron can exist in both forms. You have studied in physical chemistry that there are two types of catalysts, homogeneous catalysts, heterogeneous catalysts. For example, if I just have iron ions, and if I have an aqueous solution, iron ions will be homogeneous catalysts. If I use iron, the solid, with an aqueous solution or a gaseous solution, just like in Haber's process, that's a heterogeneous catalyst. But let's talk about why do the existence of these states help them become good oxidizing agents. We've talked about the oxo compounds, chromates and manganate, that they make them good oxidizing agents. Iron can be called as a good oxidizing agent because it's getting reduced itself. You can see this iron is getting reduced here. So it is a good oxidizing agent. Why good? Because it has a positive value. But let's look at manganate, plus 1.53. Students, it is not just the good one. It's one of the best oxidizing agents. And it tells us the color change as well. That is why it's the best one, from purple to colorless. And if we talk about chromate, it is also one of the best one. Why? Because A, it can easily involve 6 electrons. That is a good one. One chromate ion can oxidize 6 irons. It's a strong oxidizing agent. And secondly, the color change is also there. Orange to green. So that makes them good as oxidizing agents. But when we talk about their particular role as a catalyst, we use the experiments where, let's say, iron 2 and iron 3 ions. I can write them as iron 2 and iron 3 being used. So, iron is stable in both of oxidation states. That's what we talked about. That they have a good K-stab value. We'll study that concept later. But they're stable. For now, they're just stable iron ions. So if I use them in an equation in a chemical reaction. Where peroxidosulfate is there and I reacted with iodide ions. Now, the final equation will be, this would become 2 moles of sulfate ions and 1 iodine. You need to see that the charges are balanced. Here it's 2 and 2, minus 2, that's minus 4 charge on this side, minus 2 here, and 2 into minus 1, minus 4 charge. It's a balanced equation. And what do we observe here? That iodide ion is getting oxidized to, it is getting oxidized, minus 1 to 0. On the other hand, sulfur here is also getting oxidized, reduced, I believe. Why can that take place easily? Well, students, for that purpose, we use iron catalyst. Which iron catalyst? That's up to you. As I said, both of these irons are stable. For instance, let's say we use, if we have iron 2 catalyst. This is again the concept of stability, that how a catalyst can stay in its original form. What is a catalyst? A, it provides an alternate route to the reaction. B, at the end of the reaction, it is neither used up nor chemically changed. A catalyst neither used up nor chemically changed. There is a huge difference between used and used up. Used, it is definitely used in the reaction. That's a myth that a catalyst is not used in the reaction. If it's not used, what's the purpose? It is used to speed up a reaction. It provides an alternate pathway. But it is not used up, as in, at the end of the reaction, it has the same quantity and it is chemically unchanged. So, for instance, if we have iron plus 2 iron, what will happen? If we have iron plus 2 ions, they will react with S2O8. And iron here will be oxidized. And we'll ultimately get the sulfate. My apologies, this will be 2. So we can see that how iron here is oxidized and this is reduced. But now in this reaction, as you see, I said it's going to be chemically unchanged. But this was changed. From iron 2, it changed into iron 3. These are chemically 2 different ions. But you have already also studied the multi-step mechanisms. There is one step here as well. Iodide ions are still left. This particular iron is going to react with iodide ions, where iodide ions are going to become iodine, and this will be reduced back this time to Fe2. Now this iron is reduced this time, and iodide is oxidized. So we started off with Fe2, it was changed to Fe3, and we ultimately got back our 2 moles of iron 2 ions back. That is how they are stable. But what if, students? What if we have iron 3 ions? In the same reaction, how will iron 3 play its role? You can see they provide an alternate route, a different route. So this time, this was step 1, this was step 2. This time, this will be the step 1. Now this is step 1 with iron 3 ions. Iron 3 ions are going to first react with iodide and make it iodine, but at the end we have iron 2. Again, it's chemically changed. But step 2, the step 1 of the previous reaction becomes step 2 this time. And the iron 2 ions that were produced here now react with the sulfate oxo compound and come back as iron 3 ions. So iron has worked as a catalyst. It has speed up the reaction. It has provided an alternate route. It is chemically unchanged at the end, and nor used up. So having variable oxidation states, make them better catalysts. As they can receive or donate electrons in one step and do the opposite in the other. While doing that, you receive in one step, provide back in the other. You have provided it with a multi-step mechanism. You have provided it with an alternate route. So the very property where transition elements have variable oxidation states make them suitable as catalysts. So students, that is all for today. In the next lecture, we will be talking about that why and how do they make complexes. And that is the most important lecture because in the 25% of the paper, the questions regarding complexes and their stability, they may be more than half. So see you in the next lecture. Goodbye and Allah Hafiz.